Okay. Like I said, I think that this particular section is going to feel really familiar because on the one hand, let me see if I can, this is a new pen. Just give me a second. It's getting there. There we go. Okay, so on the one hand, this is going to feel like a familiar section because I assigned this homework before we had even covered it. And then some of you may have gotten in there and taken a look at some of the problems, maybe worked through with the question help. And then secondly, it's because it's deeply related to factoring. So this is a section on rational expressions. And just as a preview of what this is leading to, remember that rational expressions is just a word, a fancy word or fancy phrase for fractional expressions. That is, we've seen fractions where you just have a number in the numerator, a number in the denominator. Those are our basic fractions. And last time we saw some linear equations that had a variable in the top of the fraction, so in the numerator. We're going to be looking at things that have polynomials now in the top, the numerator, but also the denominator, and that leads to some interesting complications. But the preview here is that we are preparing ourselves to solve, and this is going to sound very much the same, rational equations. Okay, so this is basically why we're learning about rational expressions right now and sort of doing a deep dive into how to work with them. Because rational equations look very complicated. They look like this. Let's say, I'm just going to make up an equation here. So let's say 2 over x plus 1 plus 3 over x. Let's go with minus 2 is equal to, I'm going to go with 5 over x squared minus x minus 2. Okay, we're not going to solve this right now, but this is the kind of species of equation that we're going to be looking at. And right away, you can see that this thing looks really complicated because not only do we have weird fractions, we have polynomials in the denominator, right? We have a linear polynomial here, x plus 1, another linear polynomial here, x minus 2. They're different denominators. So if you were like truly trying to add these fractions, we would have to expand our notion of getting a common denominator. And additionally, this term on the other side of the equal sign is even more complicated, arguably, because the denominator here is a quadratic trinomial, right? So it's a polynomial with 3 terms, and it has a squared term in there. So we've learned a lot of things about fractions, about linear equations, about quadratic equations, and this sort of puts all of that together. And we need to not get lost when we're working something like this out. So let's look at something a lot simpler, okay? Let's explore something much simpler. Let's do this. This example is going to be 1 over x is equal to 1 over 3. Can you solve for x? Just by thinking about this problem. This quantity over here is a fraction. We don't know its denominator. And it's equal to this fraction. And we do know the denominator of this fraction. So what should x be? Can anybody?
3.
Yeah. Yeah, that's pretty simple. x should be 3, because if these fractions are equal to each other, then their denominators should be equal to each other. Okay? And there's another way you could go about solving this if you remember the multiplication property, or the multiplication principle rather, and that is that if you have 1 over x, then that's the same thing as 1 divided by x. Okay, so how could we undo division? Well, we know that multiplication is the opposite or the inverse operation. So what you could do to process this is something like this. Maybe you multiply this side by x, and you multiply this side by x. What we get there is that x divided by x is just going to be 1. And then we have 1/3 times x, like so. And then what we could do is get the x by itself, again, by using the multiplication principle yet again, to say what can cancel out 1/3. Well, if I multiply it by its reciprocal, and I do that on both sides, then that fraction and this whole number cancel out since they're reciprocals. And I get x is equal to 3 times 1, which is 3. Okay, but this logic here is just utilizing the multiplication principle. Does that make sense, or does anybody have any questions? So we've seen the multiplication principle used to solve linear equations, but now you have to do the critical thinking of asking yourself, when you look at something more complicated, how can I undo this process so that I can get my x, or the variable, isolated? Okay. All right. But I want to continue exploring this idea here. So let's think about one over x is equal to 2x. That is, I have 1. What? Can anybody see that? That's all blurry. There we go. Okay, let's think about 1 over x is equal to 2x. What this equation is telling you is that 1 divided by something is equal to 2 times something. So somehow we should be able to divide 1 by a number, and that's going to be equal to 2 times a number. And these numbers have to be the same, and these two expressions need to be equal in value to each other. Okay, so there's a lot of conditions there. It's sort of hard to think through, but we can, without actually trying to, solve the riddle of what number makes these conditions, we can just rely on our principle for solving linear equations. And again, we're going to use the principle of multiplication here. So what I could do is say, okay, let me rewrite the equation. And the first thing I'm going to do is multiply x on both sides. That's something that you can do because x is just a number. There's nothing special about it other than we don't know its value yet. Okay, so the reason why I'm multiplying x on this side is so that I can get it up from under the denominator. We basically don't want that variable underneath a fraction. Again, we're trying to solve for x equals something. So these will cancel out, and we'll just be left with 1 over here. But on this side, when we multiply x times x, we get x squared. So we have 2x squared over here. Now we're trying to sort of, we have a quadratic equation, right? So we started off with this rational equation. And that is, it has a variable in the denominator. Okay, we used the multiplication principle to cancel out the variable in the denominator. And in my head, I like to think about it as we cancel out the variable in the denominator and bring it up to the top. So now we have no fractions, but now this is changed into a quadratic equation. So we need to go about solving this quadratic equation, which is sort of related to the material leading up to test 2, solving quadratic equations. So what you might do is divide by 2 on both sides, because we need to get the x squared by itself. And so just so that this is a little bit clearer, I'm going to put the x squared over here. The 2's cancel out, and we have 1/2 over here. So now there's a couple of ways we could go about solving this, but the easiest way I can see to solve this is to use the square root property. Because we want to cancel out the square and just find out what x is. So what we might do is take the square root of both sides. When you do that, you get x to the 1 power, so there's no exponent over here, is equal to plus or minus the square root of 1/2. And I'm not going to worry about simplifying that. I'm just going to leave it alone. But that would be your 2 solutions. Your solutions would be negative the square root of 1/2 and positive the square root of 1/2. Whatever those numbers are, right? So if you really wanted to know what the value of those numbers are in a decimal sense, 1 divided by 2 here, it's about 0.7071, blah, blah, blah. Okay, but this is an exact solution. And you could check these solutions by putting them back into the original equation, and you'll see that you get the same value. So if I did 1 divided by, and I did the square root of 1 over 2, which is a weird looking expression, I get this number. And then if I do 2 times the solution, which is the square root of 1/2, these two come out to the same value. So really, this is a preview of what solving a rational equation feels like. That's not what you're going to see in R5. That's what you're going to see in a homework later on. Okay. So the one thing that is particularly interesting about these problems is that if you look at this guy, this term right here, and ignore the right-hand side. So let me sort of erase all of this. And let's really inspect 1 over x. Is there a value that we know for a fact, without solving this, without solving the equation, we know cannot be the value of x? Is there a number in the denominator that we could put in the denominator that we know cannot be in the denominator? I know it's a weird question because it's a negative. But we saw what the answer was. But can anybody think of a number here that if I do 1 divided by that number, we would have a lot of problems? Or we would break the laws of mathematics. Let me put this another way. Is there a number that you simply cannot divide by?
0, maybe. I don't know.
Yeah, that's exactly right. It's not a trick question. It's just asking you to remember that fact from the very beginning of the semester. X cannot equal 0. Under no circumstances. So let me put that in plain English, right? X can never be 0. And the reason why is because we can't divide by 0. So here are the reasons. One, and the simply put reason is that we cannot divide by 0. We just simply can't do it. It's not something that mathematicians are able to do. Okay, and the other reason is because a number divided by 0 is undefined. That's the same way. It means the same thing, but it's a little bit clearer here. That if we were to have some equation where we divided by 0 for some reason, then you've made a mistake. You're never going to get a real number because, as we can tell by our calculator friend, 1 divided by 0 gives you an error. And if you recall the definition of division, that if I have A divided by B is equal to X, what that means is that X times B is equal to A. So if I had a number divided by 0 here, and that equal a number, then that would mean that this number times 0 would give you some different number. But anything times 0 is 0, so that would be a contradiction. Okay, so that's the reason why we can't divide by 0, and that's why we have to think about what will make the denominator of these rational expressions, what will make them 0, because we want to avoid that. Okay, so we want to avoid values of X that make the denominator 0. Okay. So let's examine these problems. And we're going to ask ourselves, what X value makes the denominator equal 0? So the first thing I'm going to say is 1 over x plus 3. Let's look at 1 over 5x minus 2. And then this fourth one, 1 over x squared plus 4x plus 4. Okay, so we're sort of going to explore these as a class, but I'm going to sort of ask questions to see if I can lead us there. Looking at this first problem, can anybody just examine the denominator and think about what is the value for x? That if we plug this number in for x, it will make the whole denominator. It will turn the entire denominator into 0.
-3?
Yeah, exactly. X cannot be, so we're going to write it this way. X cannot be -3. Okay. Is anybody unclear of why -3 is the particular choice for x that would make this denominator 0? Does anybody have any questions about that? Is what I'm trying to say. Well, for something like this where you just have x plus a number or even x minus a number, you just have to, what you're doing in your brain really is like saying to yourself, okay, what is the opposite of this number that I see here? Because if I add the opposite, well, I'll get 0 because those things are going to cancel out. So like that is the simple logic that you're using here. But with more complicated denominators, you sort of can't do that simple logical trick where you just look at the problem and then say, okay, this is clearly the value that I can't use for x. So can anybody tell me what, this one takes a little bit of work, but can anybody look at this one and tell me what the value of x cannot be? So in other words, what will make the denominator equal 0 if I plug it in for x? Right, we're trying to find the value of x that if I multiply it by 5 and then I subtract 2, I get 0.
Probably 2/5.
Yeah, that's exactly right. And how'd you do that? How'd you get that?
Oh, it's because I just focus in the denominator.
To try to
Manipulate the x.
Yeah. So that's a good, your intuition there is really strong, I would say. There is a systematic way of finding that value. Okay. Now, we said that we're trying to find out what makes the denominator equal to 0. So what you could do then is just set the denominator equal to 0 and then solve for x. Okay. So this will be the process for finding what that value is. So you see, we're using some logic in addition to our linear equation principles to try to solve this problem, right? Because it's not something that you can just look at necessarily and the answer is just going to pop out at you. Rarely is that ever going to be the case in mathematics. But you can leverage what you know about what the question's asking you. You know, what x value makes the denominator 0? Well, let's see what happens when we set the denominator equal to 0 and then solve for x, because that's another way of framing the question. So if you were to solve this equation, you would subtract the 2 over to the, or I'm sorry, you would add the 2 over to the other side, and then you would divide by 5. So you would get x is equal to 2/5, right? But remember that this is the value that makes the denominator 0. So if I were to say, take 5 times 2/5, and really the denominator and the number here in the denominator will cancel out. So if we subtracted 2, we would get 0. But the whole expression is 1/0, which would be an error. So when we get this solution for this particular thing, we were going to say that, okay, this was the solution for that linear equation that helped us solve the problem, but really x cannot be equal to 2/5 for this particular fraction, because when you put it in there, it makes the whole denominator equal 0, and then you would get 1/0, and that would be a problem. Okay, that's the reasoning. Okay. We're going to do this again, right, for number 3. Can anybody look at this problem and just automatically see what the answer is going to be? What will make the denominator equal 0? If you can't, that is perfectly fine, right? We can just follow this same set of steps to solve for what the value of x that we need to make the denominator 0 is going to be. Okay, so we're going to go ahead and say this is the process. We're going to set the denominator equal to 0. And if you want, you could distribute this out. It doesn't matter one way or the other. Well, I'm not going to distribute it out. I'm just going to write it out, right? 5 times x plus 4 is equal to 0. Okay, so we're trying to solve this problem and figure out what x is supposed to be. What is the value of x that makes this equal to 0? And you might notice that this is a number times a polynomial. So we have two things that are multiplied by each other that are equal to 0. So you could use the 0 factor property here to say that either 5 is equal to 0, which we know is not true, 5 is equal to 5, or x plus 4 is equal to 0. So then that means that x must be equal to -4 in order to get a 0 in the denominator, which means that x should not be -4 for this particular problem, because then we would end up dividing by 0 and breaking the cardinal law of mathematics. Does anybody have any questions about this one, or just general questions or comments?
Yes, I didn't get it in that, because what about the 5?
So remember, the 0 factor property says that if you have two things equal to 0 and they're being multiplied, that either the first thing is equal to 0 or the second thing is equal to 0, right?
Okay.
And so the two things that are being multiplied here are this number and this polynomial. We know that 5 is not equal to 0. Like if we were to write 5 is equal to 0, that would not be true. It would be nonsense, and so we can ignore it. But x plus 4, it's possible that that could be equal to 0 if, when we solved it, if x is equal to -4. So that's why we can sort of ignore the 5. Alternatively, and so let's do that. If you wanted to take this and distribute it out to 5x plus 20 equals 0, you could do that. You would subtract the 20 over to the other side, so you'd have 5x equals -20. Sorry, 5x, not 50. 5x equals -20, and then you divide by 5 on both sides. X is equal to -4 still. So either way.
Okay, thank you. Now I get it.
Yeah.
The other way, I didn't click on my head.
Yeah, this way is, I would say that if you can remember the 0 factor property, it's super powerful in how simple it is, because it doesn't require you to do that distributing at first. We could just say, okay, ignore the 5 and then focus on the polynomial. And then that's like a much easier linear equation to solve. But if that doesn't pop out at you, that's perfectly fine. Do what feels natural. Distribute out that 5 and then solve that equation. You get to the same place.
Okay, thank you.
Okay, so now let's look at this one. We're looking at 4, which was 1 over x squared plus 4x plus 4. Okay. And I'm going to frame it this way. The question might say, what is the, here's some vocabulary. Restricted value for the rational expression. So restricted value is what you're looking out for when you do this process. Rational expression, again, just means fraction. Fraction with some variables thrown in. Okay, that's how I think about it in my head. Well, this is a more complicated polynomial in here, but the process is going to be the same. You're just going to set the denominator equal to 0. So whatever the denominator is, if you're asked to find the restricted value, you're just going to set the denominator equal to 0 and then solve that equation. It just so happens that when we do that for this particular problem, when we do that for this particular problem, we're not looking at a linear equation. We're looking at a quadratic equation. So we have to solve this the way we solve quadratics. So because I made this problem up, I chose a polynomial here that is easily factorable, or maybe not easily factorable, but it is factorable. So there are 3 methods, right, for solving quadratic equation. You have the 0 factor property, which requires you to factor first. We have the square root property, which really only helps if you have something that's, x squared is equal to a number, or something squared is equal to a number, where you don't have a trinomial. But if you don't like those methods, then the quadratic formula always works for solving a quadratic equation. So if I looked at a trinomial like this, I would either choose method 1 or 3. So which one do you want me to use to solve this quadratic equation?
3.
3.
3.
Okay, so 3 would be, you tell yourself the story of the negative boy. So x is going to be equal to negative b plus or minus. So the negative boy was uncertain of whether to go to the radical party because the boy was a square and he missed out on 4 awesome chicks and the party was all over at 2 a.m. This is definitely not the way I would have done it, but you don't have to do it the way I do it. You do it whichever way, unless the instructions specifically say something. You do it whichever way you feel is more natural. Okay, so the values here are 1, 4, and 4. So this is going to be A, B, and C. So we have negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 4 all over 2 times 1. Then we go ahead and simplify the radical part first. So this would be 16 minus 16. Okay. So 16 minus 16 would be 0. So just to show you guys, 4 squared. And really when you put this in the calculator, you need to be very careful about putting the 4 squared in parentheses, minus 4 times 1 times 4, and we get 0. So that's what's inside the radical, all over 2. Well, the square root of 0, as verified by the calculator, is just 0. So I can say that this term doesn't matter. Well, now you have negative 4 plus or minus nothing. So really, you're not adding or subtracting anything. So in this particular problem, -4 divided by 2 is just going to be the single answer, which is -2. Anybody have any questions about that process? Usually whenever a polynomial can be factored, factoring is a faster method of solving that quadratic equation. But again, we would have gotten to the same place. So we have to remember the forest for the trees, and we need to not get lost in the forest because all the trees look the same, right? Which that actually, funny story, I did get lost in the woods when I went on a run yesterday. I went and I ran something like 9 to 10 miles, and at some point of this trail run, I didn't know the trails as well as I thought I did, and all the trees started to look the same. And I came across a toy little plastic basketball thing, and I passed it, and then at some point I passed it again. So that's when I knew that I was lost. Luckily, after about 10 to 15 minutes of me just walking in one direction through wildlife trails and finding lots of deer and avoiding cactus patches, I found my way back to my original trail and I made it home safely. But that's what it feels like in mathematics when you're doing stuff like this. We've done this quadratic equation. If you're not particularly adept at it yet because you need more practice, then this can feel like, okay, when I get to this place, I'm done. But the real question was all the way up here, and what is the restricted value for this rational expression? So always ask yourself, don't just say, oh, I'm fatigued, I'm tired at this point, this must be the answer. Because that will trip you up every time, especially since I'm sort of crafting the alternative answer choices so that if you stop short or do the wrong thing, I'm going to put that as one of the answer choices. Okay. So this number is the restricted value for this expression because if I were to say, well, let me put it this way, x cannot be equal to -2 because if I have 1 over -2 squared plus 4 times -2 plus 4. And I put this expression in the calculator. I'm just going to put the denominator, right? So -2 squared plus 4 times -2 plus 4. I get 0, which means I would get 1 over 0, which would be undefined. And so I wouldn't be able to proceed with that problem. So you would say -2 is the restricted value, or x cannot be equal to -2. Okay, so let me give you guys a set of problems that I want you guys to work through. And I'll throw you guys into breakout rooms for this practice. -4 over a plus. That's a 9. I'm going to make my a's look like this, just so we don't confuse them for 9s. And also notice on those last problems that we did that I didn't pay attention to the numerator at all. I think I gave you guys simple numerators like 1 over something, but we're not paying attention to the numerator at all in these problems. We just want to see, regardless of what the numerator is, even if it's a simple number, even if it has a variable in it, we only care about checking to see what will make the denominator equal 0, because we can't divide by 0. You can have 0 in the top of a fraction all day, every day. But once it's in the bottom of the fraction, we've destroyed everything that we know about math. Okay. These problems will say something like find the restricted value. Or it'll say find the domain of the rational expression. Okay, and I'll talk about what we mean by domain after we've found the restricted values for these problems. Okay, so let me give you guys about 10 minutes. Let me throw you into breakout rooms. Once the invitation goes out, just go ahead and accept it like normal. And invitations have gone out. Please accept the invitation to those rooms. I'm always muted. Okay. It seemed like you guys were able to get through those. Does anybody have any questions or comments, or concerns about those particular problems? Because it seemed like it was pretty straightforward for you guys, for both groups. But if anybody, was feeling self-conscious in the group and was afraid to speak up, but still has questions, now's the time to go ahead and ask them. Okay, so when you're solving a problem like this and they ask you to find the restricted values, it's going to be that process that we've been going through. You're going to set this denominator equal to 0. You're going to solve that, and we should, in this case, get a is equal to -9. I'm going to put a little negative right there. Okay, so a lot of times what I'll do is I will put that a equals -9 is the restricted value in my notes. So whenever you see RV, it's restricted value. That's the same thing as putting that a cannot be equal to whatever the number is for that particular problem, okay? So if you label it as a restricted value, you could say that the restricted value is equal to this. Or if a lot of times when they ask about the domain is going to be written in such a way that they'll say x, the value of x is such that x cannot be equal to, I'm sorry, whatever the variable is. In this case, it's a. I'm sure that we all do this thing where we accidentally change the variable to x. But a is a number such that a is not equal to -9. This is called set builder notation, and it's the way you'll see it in MyLabs Plus. But the only thing that you have to worry about typing, in is this part right here. A is not equal to -9. They'll give you the brackets and then this little vertical line. This is just like a compact mathematical symbol, right? Math in a lot of ways is a foreign language. And if a mathematician were to read this, they would read it as the set of all numbers a such that a cannot equal -9, which is long-winded, but that's why the compact notation is really useful for mathematicians. And we could think about this domain on the number line if we wanted to. I don't think that there are any problems like this on this particular homework, but if you wanted to graph what the values of a could be and could not be, then you would think about the number line, and it would be from -infinity to infinity, like normal. And I know that this -9 is a number of interest here. And this is sort of connecting it to those linear inequalities we were looking at last week. Well, if I know that -9 cannot be a solution, that means that this value is missing. So I'm going to put an open circle there. If that value is missing, then every other value is perfectly fine. The only value that we're excluding or that's restricted is the -9. So you might ask yourself, how do I write the domain in interval notation? Well, you might not ask yourself, but I would ask myself, how would I write this in interval notation? And it looks a little bit strange because it looks like we have to skip a number in the middle of the number line. Like if we just looked here and wrote this part in interval notation, it would just be parentheses -infinity all the way to -9. And then we put a parentheses on the -9 because it's not included. But on the other side, it looks like we start at -9 and then go to +infinity, and we put parentheses on -9 because that's not included. So it's like there's a gap in the middle of our number line. So to join these two intervals together, mathematicians will put this U symbol here. This U symbol is called a union and joins two intervals together whenever there's a gap in between them. And so when we take our deeper dive into rational expressions and rational equations, we're going to see the domain is equal to this thing, and we'll have to get used to writing it. In this particular homework, I'm pretty sure that this is all they're going to ask for, but I just wanted to give you this as a preview. Okay, the other ones, let me skip to another piece of paper. Number 2 was a minus 3 over 7 minus a. And again, you guys did a perfectly wonderful job by saying, okay, ignore the numerator here. 7 minus a is equal to 0. You solve that, and you move the a over to the other side, or you move the 7 over to the other side, whichever procedure. In any case, I know that a, in this case, cannot be equal to 7. So in MyLabs Plus, the domain of this expression, that is all the values that are going to be valid for this expression, would be all of the values of a such that a is not equal to 7. Again, you would just have to write it like this. And then if you wanted this in interval notation, the domain in interval notation, you can think about that number line from -infinity to infinity. +7 is right here. And then +7 is excluded, so I'm going to put a little open circle there to indicate that it's being excluded. But everything else would be a perfectly fine value to insert into this expression. So the domain in interval notation would be -infinity to 7 union 7 to infinity. So it's like this restricted value is cutting our number line into two parts. The part that's below 7 and the part that's above 7, but we know that we have a gap here at 7 since we cannot use that value in this expression. Any questions about this? Okay, and then the last one was x squared minus 64. So this one was like deceptively confusing, I think, or it looks a little bit complicated, but it's a lot less complicated than you might think. So remember, we're just focusing on the denominator, right? We're not focusing on the expressions that have a variable, because just like in this problem, we were only concerned about the denominator. We didn't care about the numerator at all, okay? Then we set that guy equal to 0. And then there are two ways of approaching this. You could have put it into the quadratic formula, and I think that this one's factorable, so I'm going to factor it. I would have used the AC method. I would have factored this into x minus 1 and x minus 5 equals 0. Then you can use the zero factor property to say x minus 1 is equal to 0 or x minus 5 is equal to 0. And then that's x equals positive 1 or x equals positive 5. So the restricted values here, or the domain, is that we can use any value of x such that x is not equal to, and then you'll put it as a 1, 5. X cannot be equal to either of those values. And that's the way you would type it in to MyLabs Plus. The domain and interval notation, though, is a little bit trickier here because there are two values. So you can think about the number line extending from negative infinity to infinity. And we have a value of 1 here and a value of 5 somewhere over here. It's bigger than 1, so we put it to the right side. And we know that we're trying to exclude both of those values. But now, because we have two gaps in the number line, we really have three regions or three intervals. We have this region here. I'll shade the middle region with purple just so you can, clearly see that it's a separate region. And then the region on the right, which is from 5 to infinity. So as you might be able to guess, the domain and interval notation here has to include or describe all three of these intervals or all three of the regions. So this region is from negative infinity to 1. This region here is from 1 to 5. And then this region over here is from 5 to infinity. And we can join those since they're separated by gaps. We need to join them with the union symbol. Does anybody have any questions about that? Okay. So I know that we're probably feeling like we're ready for a break here in a little bit, but I want to finish up this topic of rational expressions because there's one more kind of problem that you're going to run into for the homework before we go to the next topic. So let me do, you know what? I think it'll be better if we take two smaller breaks. So let's take a 5-minute break right now. And then I'll cover the rest of the rational expression stuff. And then when we're done with that, we'll take another 5-minute break and then switch gears to the next topic. Okay, so let's take a break. Just stand up, stretch, get some water, do what you gotta do, get some sunlight. Okay, how are you guys doing? How are you guys feeling? Any questions, comments, concerns about the topics that we just covered or about life in general? Just want to be able to decompress a little bit in between some of these heavier or step-heavy processes. Not all at once. Maybe we're still waiting on people to return. Did anybody have any questions about these, or did these seem pretty straightforward?
Yes.
Okay. Cool. Okay. Well, let's move on then. You know, I introduced this topic of rational expressions, you know, with that preview that we're going to be seeing some rational equations. And let's see. Let's look at that preview again. Rational equations. So in some of these equations, we might have something like, let's do 7 over x plus 3 plus 4 is equal to x. And, you know, I don't expect you guys to get this process down right now, but I want to show you what the process is going to look like so that you have a feel for it when we actually encounter them. Okay. So when you look at something like this, the first thing you're going to feel is a lot of anxiety because you're like, what even am I looking at? But that's okay. That's completely natural. Those feelings are valid. First thing you do, you take a deep breath. And then after you've taken your deep breath, you ask yourself, okay, what am I trying to do here? Or what kind of equation is this? Because usually that'll tell you what the first step is. And usually the first step of a rational equation is that you want to cancel out, well, actually, step 0 is you want to identify restricted values. Right, so ignore step 1, which is only partially written right now. The first step, step 0, is to identify restricted values. So what you need to do is be able to look at these things and say, okay, this is a term. This is a term. And then I have a term on the other side of the equal sign. So there's 3 terms in this particular problem. The only terms that are going to generate restricted values are those that have a variable in the denominator. So this is a whole number 4. We don't have to worry about this being a variable value. It's never going to change because it has the value of 4. Okay. I mean, we can manipulate it. We can change the equation if we wanted to by using, you know, the multiplication principle or the addition principle, what have you. But this number does not have a variable attached to it. Okay. This term over here has a variable, and we need to find the value of whatever x is. But we're not running into any problems where we're dividing by something that could potentially give us 0. Okay. So the only term here that is going to generate a restricted value is this one, because in the denominator you have a variable expression or a polynomial where some value of x could result in dividing by 0. Okay. So in this case, you might identify, you know, through the process that we just went through, that the restricted value is that x should not be equal to -3. And we have to hold that information to the side as we go about solving an equation like this. Okay, so we identify the restricted value. Then the first step after that would be to cancel out the denominator of any fraction that has variable expressions in the denominator. So let's think about this for a second. Let's think about the one term, 7 over x plus 3. What could I multiply by this first term so that I cancel out the denominator and I'm just left with 7?
X plus 3.
Yeah, exactly. And a lot of students will say x plus 3 over 1. It doesn't matter if you put it over 1 or if you just have it as x plus 3. A lot of students like to have a fraction times another fraction that feels more natural to them, but I would have just put x plus 3 perfectly fine. And that is exactly right, because remember, if I was to multiply this out, I would have 7 times x plus 3 on the top, and I would have x plus 3 times 1 on the bottom. And any number divided by itself, or in this case, any polynomial divided by itself, will simply cancel out. So you would have 7 over 1, which is just 7. So similar to when we were solving those linear equations and we wanted to cancel out a numeric denominator, what I have to do is say that for this particular problem, the LCD that I'm going to multiply, the least common denominator that I'm going to multiply by every term, is not a number, it's a polynomial. I'm going to multiply this by each of these terms. Okay. So what I like to do is write the problem out again. I know it's a lot of writing, but I think it's super helpful. So I'm going to put the 4 here. I'm going to put a gap equals x. And then I'm going to multiply the LCD into the problem. So each term, this term gets multiplied by x plus 3. This term gets multiplied by x plus 3. And this term gets multiplied by x plus 3. Now I know that that looks strange. It feels strange, but it is fundamentally the same thing as multiplying a single number by every term. Okay, just like we did last week where we said, okay, find the LCD of 4 and 5 and multiply 20 by all of the terms, or whatever the LCD was. That's what we're doing here, and we're doing it with a specific purpose. And the reason why we're doing this is because for this particular term, we're going to cancel out the fraction, because this times 7 over x plus 3. If you're multiplying by x plus 3 and dividing by x plus 3, those cancel out, and you're just left with 7. And not having that fraction is going to be super useful. On the other terms, like 4 times x plus 3, there's nothing that cancels out. So you do have to distribute this out to get 4x plus 12. Over here, you will have to distribute out the x times the other polynomial to get x squared plus 3x. So at this point, I know it feels like a lot more steps than just 3, okay? But we've canceled out the denominator here, and now we have an expression that doesn't have any fractions. So if I look at this expression, there's a lot of terms. Maybe I want to collect them all to one side. I can tell here that because I have an x squared term, it's a quadratic equation. So on this step, sometimes you get an x squared, sometimes you just get an x to the power 1. And so depending on whether you end up with a linear equation or a quadratic equation, that will determine what the next steps are. So in this case, we solve a quadratic equation. And to solve a quadratic equation, you have to get everything on one side and get this in standard form. So what I would do is combine some like terms just to clean some stuff up. This combines to be 19. So we have 4x plus 19 is equal to x squared plus 3x. I would move these two terms over here because I like to keep my x squared term positive. So I would end up with x squared. If I subtracted 4x over here, I would get minus x. And then if I subtracted 19, I would get negative 19 is equal to 0. So the steps for a quadratic equation are make sure that it's in standard form. You have 3 strategies for solving that quadratic equation. I don't think that this one is factorable, so I would use the quadratic formula.
The x squared wouldn't be negative x squared?
I'm moving these terms over here
Okay.
to keep the x squared positive.
Okay.
I know that it seems weird because like I probably should have just said 0 is equal to this. But I flipped it around because I think it's more natural to have the quadratic on the left-hand side. So once you move something around, it could be negative, if you move these guys over here, but I like to keep my squared term positive, right? Either way, it'll lead to the same answer. Okay, you just have to be careful with the quadratic formula. That's where the mistakes are going to happen. Okay. So we would solve this quadratic formula, but really I'm just going to stop here for now. So this, I'm just going to put to be continued because this isn't the point that I'm trying to make. The point that I was trying to make is that in this process, we had to cancel out the denominator here and we had to acknowledge the restricted value. And then we had to cancel out the denominator by multiplying this rational expression sort of by its reciprocal, really just multiplying by whatever the denominator was to get those to cancel. And so in some sense, that's sort of like reducing a fraction. Okay, so we'll pick back up on this problem later, probably on another day. But we are going to simplify rational expressions just like fractions. Except the factors that we're going to cancel will be numbers or polynomial expressions. So we're gonna build up to something that's clearly more complicated, but I want to give you some examples and walk you through those and then get you some practice. The instructions might say something like write the rational expression in lowest terms. And so you'll hear me refer to these as write the expression in lowest terms or simplify the fraction, simplify the rational expression. Those all mean the same thing. So maybe we could do -4 times y minus 4 all over y minus 4 times y minus 1. So we're just simplifying this expression. Can anybody look at this expression and then determine what the simplified form of it is? In other words, can you cancel out one of the factors here?
-4 over y minus 1.
-4 over y minus 1. Yeah, that's exactly right. That would be the simplified form. So what you might say to yourself when you're looking at this is that you have this factor times this factor on the top. And you're dividing, in some sense, this factor and this factor. Well, since you're multiplying by this factor and dividing by it, well, it's just much easier to say that those cancel out. Or that since y minus 4 divided by y minus 4 is just 1, those cancel out. So you would just be left with negative 4 over y minus 1. And this would be the answer. Does that make sense? Okay. Well, sometimes the fraction or the rational expression is already going to be in factored form. There was no work that we had to do here except for identify that these common factors could be canceled out. Okay, so in other problems, like 5x minus 15 over 2x minus 6. Can anybody just look at this problem and sort of identify how do we simplify it, or what would the simplified expression be? Does anybody have any guesses?
It could be that 5 entre parentheses x minus 3 over 2 parentheses x minus 3.
Yes.
And
Okay, good.
X minus 3.
So here's an important note. You can only cancel factors. So that means that we have to factor out the polynomials first and then examine if there are any common factors, right? Just like with fractions, you know, we introduced at the very beginning of this semester that if we wanted to reduce fractions, we could use prime factorization to factorize the numerator, factorize the denominator, and then cancel out common factors. That's the same principle here. A lot of times students will make the mistake of trying to cancel out these terms by saying like, oh, 5x divided by 2x, the x's cancel, or something like that. But because these are not factored, you cannot cancel anything yet, okay? So you have to first factor out the 5 on the top. So you would have x minus 3. Then you would have to factor out a 2 over here, x minus 3 there. And then you can cancel the common factors, since this factor and this factor, once it's divided by itself, is just 1, you would have 1 times 5 over 2, which is just 5 over 2. So it turns out that this scary polynomial expression or rational expression is just a single numeric fraction. Okay, so we need a factor, and then we need to cancel common factors. And I'll tell you this, that if you factor and then you get a bunch of factors and nothing seems to cancel, you probably factored wrong. Okay, so just go back to the top and try to factor those polynomials again. Okay, let's look at something else. Another one where we have to factor the expressions. (16x to the third power plus 4x over 20x squared). Whoop, there you go. So can anybody factor the top, the numerator of this fraction? What is the greatest common factor? If we just ignore the denominator, what would the greatest common factor here be?
4x.
Yeah, 4x. And so we'd have to multiply that by something. What would go inside the parentheses?
4x squared plus 1.
4x squared plus 1. Perfect. Okay, is everybody okay with that? Over 20x squared. Okay. But if you wanted to, here's something that you could do. You could factorize this, even though it's not really like two terms like this. We wouldn't be able to factor the greatest common factor here, but we could factorize the 20 and we could factorize the x just so that we can see all of the factors that are participating in what was at one point multiplication. So what I would say is that this is 4 times 5 would give you the 20 times x gives you the x squared. Because then we can say, okay, cancel common factors. The common factors are 4. And then we have an x here and an x here. So if we cancel those, what are we left with? Well, we have 4x squared plus 1 on top and 5x on the bottom. And you're going to feel tempted to continue canceling stuff. But we have 2 terms on the top and only 1 term on the bottom. So we cannot cancel terms. We can only cancel factors, things that are being multiplied or divided. So since there's nothing else that's being multiplied on top, it's just being added, we sort of have to stop here.
What if you would have canceled your 4 and your x and your x?
You're talking about up here?
Yes.
Well, the reason why you can't do that is because even though there's a 4 and an x squared here, those are being multiplied, right?
Oh,
These are being added.
okay.
So this isn't 4x squared, even though it looks like it. It's actually 4x squared plus 1. So let me put that in a different light, right? If I had 4x squared plus 1 and I divided it by 4x squared, you sort of get this sense that maybe you could cancel. So let me put this note. Don't do this. Okay. This is extremely important that you don't do this because it happens every semester, probably at every school where they teach math. Students will want to do this, and then they'll say that this is just 1. But that's no bueno. Okay, and the reason why is because let's say that x is equal to some concrete value. It's some concrete number. I'm going to choose 2, just arbitrarily choosing the number 2. Well, if this was true, that I could simplify like this, that means that if I plug in that number for x, I would be able to simplify it to 1. So 4 times 2 squared plus 1. 4 times 2 squared. So we're just going to go through the process and just simplify it using an order of operations. So this would be 4 times 4 would be 16 plus 1. And then this would be 4 times 4, which would be 16. Well, that would be 17 over 16, which is not 1. It's close. But it's actually 1.0625. And it turns out that for any value of x, you wouldn't be able to simplify like this and get the same value. So the main takeaway is that this is a polynomial factor. You want to cancel out polynomial factors or individual factors. But if it's in parentheses and you've already factored stuff out and it looks sort of similar to what you see out here, just leave that stuff in parentheses alone. Because you've already factored, you're going to cancel out whatever factors you've taken out. Okay, let's look at another example. Z squared plus 10z plus 25 over z squared plus 6z plus 5. Okay. Well, again, just as a note to, so that you don't get confused, right? The instructions tell you what you're supposed to be doing. I know that some of you will go into the homework or on the test, will say, okay, I'm just going to set the denominator equal to 0 and then solve it because that's how we found domain earlier. But that's not what these questions are asking. These questions are going to ask you to simplify the rational expression. And that's different from find the domain or find the restricted value. Okay, so make sure that, like, in your notes before you go into a quiz or go into a test, that you know what the question is asking or what it is requiring of you before you go in and just do something that you randomly remember that we did that in class at some point. Okay, because the numbers and stuff look the same, the problems look the same, but depending on how the question is asked, that will determine what process or what strategy to use. Okay. Okay, so the process that we're using here is factor the numerator and the denominator. Then we're going to cancel common factors. And that's it. That is the process for simplifying a rational expression. Now, some of these rational expressions have a lot more scratch work than others. So what I'm going to do is, this one actually has a lot of scratch work. I'm going to divide my paper into 2 parts, because first we need to factor the numerator. Then we can move on to factoring the denominator. So you have to get adept at organizing your workspace on the page, right? If you're still trying to squeeze all of the work into a small piece of paper, like small portion of the paper, then at this point, you're doing yourself a grave disservice, because some of these problems do require a lot of pre-processing before you actually get to solving the problem. So the first thing I would do is write the numerator, which is z squared plus 10z plus 25. You're going to factor this using the AC method because it is a trinomial. So I would say that first you start by multiplying 1 times 25, and that would be 25, right? You look at the factors of 25, 1 and 25, and 5 and 5, and you'll choose these so that you can break up the middle term into 5z plus 5z. So we have z squared plus 5z plus 5z plus 25. You factor that by grouping. So these two have a z in common, z times z plus 5, and then this would be 5 factored out, and z plus 5. So once I complete the factorization, I have z plus 5, 5 times z plus 5. So that's my numerator. So if you're still struggling with the AC method, it's not going to go away. And I can tell you this, it's not going to go away for the rest of the semester. So at some point, you need to get it down. Come into Math World, we'll work on factoring, okay? The denominator, z squared plus 6z plus 5. We're going to do the same thing. Use the AC method. So we have a 1 here, and we're going to multiply 1 times 5. So that's just going to be 5. 1 and 5 are the factors of 5. So then we're going to break up the middle term into 1z, or just z, plus, oh, that's funny, 1z. Anyway, 5z. And then we'll bring down those other terms, plus 5 plus z squared. From the first two terms, we could factor out a z, so we get z plus 1. From these two terms, we can factor out a 5, so we'll get a z plus 1 there. And then we factor that into z plus 5 and z plus 1. Okay. I'm going to let you guys catch up to that, and I'm going to take a swig of water. Does anybody have questions about the factorization? Okay. Well, the original problem is that we need to simplify this rational expression. So this is going to be our new numerator. This is going to be our new denominator, and you have to be very careful to put those in the correct location. Okay, this goes on top. So we'll have z plus 5 times z plus 5 on top. That was the numerator. Divided by z plus 5 times z plus 1. That's the denominator. And then you cancel common factors. This cancels with this. And once you've canceled factors, that's pretty much it. Z plus 5 remains on top over z plus 1. And for the love of God, please don't simplify any further, because this is done. This is it. Don't go any further. Okay, does anybody have any questions about that? Okay, this is going to take a lot of practice, but I'll open up the homework for that here in a little bit. Let's take a 5 to 7 minute break, and then we're going to move on to something else. Continue recording. We're shifting gears here a little bit because we're no longer talking about rational expressions, although those are going to continue to be relevant. What I'm trying to do is prepare us for the whole, let's say, zoo or buffet of other types of equations that we're going to have to be able to solve coming up pretty soon. Next time we meet on Wednesday, we're going to look at 4 different kinds of equations. That is, in addition to linear equations and quadratic equations, we're then going to have rational equations that we're going to go over, radical equations, which is why we're simplifying radical expressions here, just as a review. So what did I say? Rational equations, radical equations, equations with rational exponents, and then something called quartic equations. So that's going to be 4 more types of equations in addition to the 2 we've already done, linear and quadratic. okay? But usually for 3 of these types of equations, they'll turn back into either a linear or a quadratic equation. So you have to be prepared with all of your tools now, right? I said at the beginning of the semester that college algebra is tougher than maybe your English or psychology class because you can't fake it. And what I meant by that is that we're accumulating a set of tools that at each turn of the corner, we're going to need all of those tools. And I don't know if I've used this analogy in this particular class, but I often tell my students that when you go to Home Depot or Lowe's or whatever your big box store is to buy a tool, say that you need to hammer in a nail into a 2x4 at home, and you go to buy that hammer, you don't use the hammer and then throw it away and forget about the hammer, right? Because you're going to need that tool later when you have to hammer in more nails. Similarly, if I was doing a woodworking project, I wouldn't go to the store, buy a circular saw, and then once I'm done cutting all of my wood, throw away the circular saw and then have to buy a new circular saw every time. Like that just doesn't make any sense. The tools that you're given here in math to be able to identify these different structures or objects that we're working with, polynomials, factorization, those tools, you're going to need them again. That's what I meant by it all accumulates, okay? So don't throw away your tools. Now, if you have found yourself in a position where you feel like you've thrown away some of your tools, that's why I keep inviting you guys back to Math World, okay? So to preview the sorts of equations that we're going to get into, we're going to be looking at radical equations and equations with rational exponents. So let me sort of number these just so we can see what they look like. So 1, and then equations with rational exponents would be 2. So on the one hand, we could have radical equations that look something like the cube root of, let's say, x plus 1 is equal to x minus 7. Well, we might have an equation that looks like this, and we'll have to remember what we need to do to cancel out the radical symbol, okay? Similarly, we might have an equation that looks something like this, maybe 3x minus 9 raised to the 5/4 power is equal to 17. And we've seen in quadratic equations when we had something raised to the 2nd power that we could just take the square root of that, right, to cancel out the 2nd power. So we're going to have to think a little bit more deeply about how do we cancel out this rational exponent. And remember, rational is just another word for fraction. So when a particular polynomial or an expression has a fraction exponent, how do we cancel out that fraction exponent? Okay, so that's where we're going. But right now, we need to recall these particular properties of exponents and radicals. Okay, recall the properties of exponents / radicals. Because remember, radicals are exponents. The first property is that if I had, let's say a, some expression raised to the 1/n power, that is the same thing as the nth root of a. And I think that a lot of times when we write this expression with an equal sign, it doesn't convey exactly what we intend to convey to students. And what I mean by that is that if you have something that has a rational exponent, you can convert that into a radical expression. And if you have a radical expression, you could convert that back into a rational exponent if you want. These two things are two ways of writing the same kind of object. So for instance, if I wanted to, well, let me introduce this second, more familiar or more common property, and that is that if we have something raised to a fractional power where the top of the fraction is not 1, then that's equal to the mth root of a to the nth power. So what I'll say is this, that the numerator of this fraction, this fractional exponent, is the power, and we have that over here, a raised to that power. And the denominator of that fractional exponent is the root. So that goes out here. So for instance, when I'm trying to solve something that looks like this, we'll get to the place where we could naturally just convert this, if we wanted to the fourth root, because it has a 4 here, the fourth root of 3x minus 9 to the 5th power, if we wanted to. And that's equal to 17. And then maybe it'll be easier to solve it that way. But maybe not. We just need to be flexible with, can we convert it to this thing, and will that thing be easier to solve? Similarly, if I know I have a root here, a third root, then the nth root can be 1 over n power. So I could convert this to x plus 1 to the 1/3 power, if that's helpful, to continue solving that equation, right? So I just wanted to demonstrate that these properties are going to be super helpful when we're solving these kinds of equations next time. But that's not where we're starting. We're going to start at a much lower level in terms of difficulty. So we're going to use those properties. And what I want you guys to do is just work on these practice problems. And let me go ahead and grab these. And the instructions will say simplify by converting to rational exponents. So we're going to simplify an expression by converting to rational exponents. And the first expression that we're going to look at is the square root of 2 to the 4th power. Okay, so there's a couple of ways you could solve this. There's the long way, I would consider it the long way, by writing this as 2 squared times 2 squared, and then taking the square root of those and canceling out the squares. You could do that. That's perfectly fine. That logic makes sense. But we're going to just use our property of radicals and exponents and say that if we have and we have the square root of it, that's going to be the same thing as a to the 1/2 power. Because remember, the square root has an understood index of 2. And just like to expand this notion, right, if I had the cube root of something, that would be something raised to the 1/3 power. Okay, so we're going to simplify by first converting this to rational exponents. So what I want to do is, I know this guy already has a power. And I know that this is the square root of whatever is inside here. So what you could do is write this as 2 raised to we have the 4th power and the 2nd root. Okay, now can we, even though this is an exponent, it's a fraction inside the exponent. Can I reduce 4 over 2? Or maybe you think about it as 4 divided by 2?
2?
Yeah. So I've simplified the rational exponent to just a 2, and now I know that this is just 2 times 2. So the answer to this question is 4. But we first wanted to go through this intermediate step here. In MyLabs Plus, they'll break it up into 2 steps. You're going to convert that to a rational exponent using this property over here. So you'll put this in. And then, or maybe you'll simplify it. And then you'll put the actual answer, evaluate what the simplified form is. Okay, so let's look at another problem. Some of them won't be numeric, they will be variables. So we'll have x to the 48 here. Can we simplify this by first going through a rational exponent intermediate?
Do we do the same, like 48 divided, okay, x over 48 divided by 2?
Yeah. Yeah, because again, if I have x and I have the square root of that, that's going to be x to the 1/2 power. So if I have the square root of x to the 48, that's going to be 48 over 2. And then we could simplify that and call that 48 divided by 2 should be 24. And since this is not a numeric value or expression, we don't know what the value of x is. So I don't know what x to the 24th is. So we're just going to leave it like that. That's as far as we can go. Any questions there? Okay, let me give you a set that you guys can work. Here we go. Let's do the cube root of x to the 12, the 4th root of 3 to the 20th, the square root. No, I'm going to make the 7th root of z to the 14th power. Yeah. Does anybody want to walk us through this first one?
It could be like the x power 12 divided 3.
Yeah. Which would just be what?
Will it be 4?
Yeah, it would just be x to the 4th power. Not too bad, right? Like you guys don't have to be timid about this. I know the last stuff was a little bit intimidating, but the property here is pretty straightforward, right? There's no trick questions. We're just going to do a straight application of that property. So what can somebody walk me through this one?
Would it be x 20 over 4?
Well, it wouldn't be x, right? Because
Oh,
we don't have.
three, sorry,
Yeah,
three.
yeah, there we go. 3 to the 20 over 4 power. And can we reduce that power?
5.
Yeah, it would just be 3 to the 5th power. And then since this is a numeric expression, we don't want to spend our time multiplying 3 times 3 times 3 times 3 times 3. Is that enough threes? We're just going to put 3 to the 5th power in the calculator. 243. Are you guys okay with that? Any questions? Okay. What about this last one?
Would it be z to the 14 over 7?
Yeah.
Z squared.
So then 14 divided by 7 is just 2, so we have z squared, and that would be the simplified form. Not too bad, right? Okay, let's look at some others. So that was taking a radical expression here, using that property to convert that to an expression with rational exponents, and then simplify. That's the basic process for that. Now we're going to go in sort of the opposite direction. We're sort of going to have an expression that has a rational exponent, but convert that to a radical expression, and then simplify that if it's possible. Okay. Okay. So we're going to write in radical form then simplify. So let's look at these problems. 289 to the 1/2 power. Now here we have to recall that same property. Before we were saying that if we had the square root of something, that was something to the 1/2 power. So it doesn't matter if you write this with the square root first, or if you were to write a to the 1/2 power is equal to the square root of a. Whenever you have an equal sign, that goes both ways. Okay, so don't let that trip you up. With something like this, we could easily just convert that using our property to the square root, because that's what's here. Remember, this is the root. So we're taking the square root of 289. And then if that's a perfect square, we can just put that into the calculator. So let's see. I'll always check the calculator first, just to cut down the amount of work I have to do. So the square root of 289 turns out is just 17. So that's the answer. We had to go through a radical intermediate first, and then we could simplify that numeric expression. Okay, what about this one? Can you guys solve this one?
Nine E.
So I was waiting for the train to leave. Yes, that would be correct. Now, if that's confusing to you guys, it's because she said E, which is Spanish for I, and that makes perfect sense.
I'm so sorry. Yes, exactly.
No. I just wanted to clarify in case that confused any of your classmates. I understood what you meant. Y, yo understood what you meant.
Sorry.
No, it's fine. It's the beauty of being bilingual. Okay, so we're going to just use the same property here. We're dealing with 1/2 power, so that denominator on that power is the root. So we can call this the square root of whatever the expression is inside the parentheses. In this case, it's a negative 81. But remember that when you have a negative of a square root of a negative, and really it's the even root of a negative. So it could be the 4th root or the 6th root or the 8th root or the 122nd root. If it's an even root, you're going to get an imaginary number. So in the past, I said that it might be just useful to pull that out, call that an I, and then the square root of 81 is simply 9, so we can call this 9i. 9i would be the principal root. Technically, that should be a plus or minus. I'm going to put plus or minus. But you know what? I will tell you this, that sometimes MyLabs Plus is a little bit finicky about these answers. So if it's not both, then just put the principal root. So the principal root is the positive root, which in this case would be 9i. Are you guys okay with that one? Or are there any questions there? Okay, time to throw a wrench into things. I'm going to do one more. Well, we'll do a couple more, but this one I think is a little bit confusing to students. Even though we're continuing to use the square root, how many of you think that this is going to result in an imaginary number? If we were in the classroom, I would look out to see some hands raised and some hands down. I really miss being in the classroom. Does anybody think that this is going to result in an imaginary number? Okay. Either there are some people that are timid and do think that we're going to get an imaginary number, or everybody is correct and thinks that we won't get an imaginary number. But let me explain to you why that is. Whenever we have an exponent onto parentheses like this, the exponent sort of belongs to everything in parentheses. That is, the parentheses is sort of indicating ownership of that exponent. However, the minus sign is not, it's outside of the parentheses. So really, this is the only thing that gets that square root. Okay, so be very careful with that. We have a negative on the outside, and then this rational exponent expression is the square root of 49/4. And then you could call this negative the square root of 49 over the square root of 4, which remember from a few weeks ago, we had, if we have a over b and we're taking the square root of that, you can split up the square root like so. Well, then we can simplify the expression to just be 7/2. But don't forget the negative on the outside. That'll be super important. Any questions there? Okay, let me give you 2 to answer on your own. 27 to the 1/3 power. Let's go simplify that. And then 625 to the 1/4 power. So take about 3 to 5 minutes to solve these guys. I know it hasn't been 3 to 5 minutes yet, but has anybody solved this one yet, or simplified it rather?
Is it 3?
Yeah, I think so. And there's a couple of ways of going about solving this. The simplest way is probably taking and calling this the cube root of 27. And remember, the cube root is asking what number raised to the third power gives you 27. You could also just put that in the calculator, since the calculator does have a cube root. Math, cube root of 27. And a lot of times I just put things in the calculator so that you guys have a sense of resolution, like that is true, the calculator has said it, the calculator has decreed that this is a true statement, this is just 3. The alternative way to solve that would be to recognize that 27 is 3 to the third power, and then that's being raised to the 1/3 power. Since we have a power to a power, we multiply those powers. So 3 times 1/3 is just 3 to the 1 power, which is just 3. And then what about number 5? Number 5.
I got 5 for that one.
Yeah. And,
Yeah.
and you could just straight up apply this into the calculator. This is the 4th root of 625. Jeremiah, is that what you ended up doing?
Yes. Mhm.
Yeah. So we'll just go into the calculator, force it to make a 4th root of 625, and you just get 5. The alternative method would be to recognize that 625 is equal to 5 to the 4th power. So we could call this 5 to the 4th power raised to the 1/4 power. And then those powers, since they're reciprocal powers, cancel out. So we just get 5. Either way, I'll write here alternative. So that's an interesting note, though. So I do want you guys to note that reciprocal powers cancel out, because that's going to be super useful next time. should like really emphasize this. We'll talk more about that next time. Let us see. Okay, I know that we covered a lot today. So what I'm going to do is later today, I'm going to go ahead and put a quiz together. So, and break the quiz up into, it's going to be a 10-question quiz, because going into test three tends to be, I think, the hardest quiz of the hardest test of the semester. Not because the topics are particularly complicated, but because now we're having to remember different strategies for solving different kinds of equations. Okay, so I think that we're going to need that quiz for practice. So it's going to be a 10-question quiz, probably 2 questions on 5 different topics that are leading up to these equations we're going to solve next time. But I'll make it so that it is that you can take it in an unlimited amount of times, just so that you can get the practice, and also so that that grade, you can get a little bit of padding in terms of that quiz grade. Okay. If you have any questions, I know that some of you guys might feel overwhelmed at this point. What I don't want you to feel is like that you're so far behind that you can't get caught up. Right now is the time that if you are feeling like you are drowning, you sort of have to throw yourself a life preserver. And what I mean by that is you need to reach out to me so that we can do what we need to do, whether it's one-on-one tutoring in my office hours or tutoring in Math World, just to get you where you need to be, okay? Because this is college. You guys are monitoring your own grades. You're responsible for your own grades, the work that you put in. And this thing isn't gonna just magically, turn into the grade that you want. You got to put in the work, and I'm here to support you, provided that you're communicating with me, okay? So just make sure we're keeping that open communication, because I do want you to succeed, and I am willing to take, my time out of my evenings or my weekends to make sure that you get that one-on-one tutoring if you need it, okay? So don't be ashamed to step forward and say like, hey, I need help. I feel like I'm falling behind. I am here. Send me a message. Please do that, okay? That's all I got for today. So if you have any questions, you're more than welcome to stay behind and chat with me for a bit. But otherwise, go on with the rest of your day and make sure that you make time to work on these homework assignments.